Okay, so in these videos, I'm going to be going over chapter 3.6 and 3.7. So this video will start with chapter 3.6, rational functions. So we've seen some examples of some rational functions before. So the formal definition is that it's a quotient of polynomial functions of the form f of x, where we have p of x over q of x, and our p of x and q of x are polynomial functions. So the domain is going to be the set of all real numbers, basically except the values that make the denominator 0. So in this example, we're going to find our domain. So our g of x is x over x squared minus 9. So for a, we're going to say the denominator is 0 if x is plus or minus 3. As we have x minus 3 and x plus 3 in our denominator because of the difference of two squares when we factor it. So our domain is, in set interval notation, is negative infinity to negative 3 union with negative 3 to 3 union with 3 to infinity. And for b, we have f of x equals x plus 3 over x squared plus 9. And this doesn't equal 0. And nothing causes it to equal 0. That's a real number. And so we have our domain as negative infinity to infinity because we can't factor the bottom unless we're doing complex numbers. So that's why we always have a 9 here plus some value. That's always going to be positive, so it's never going to be 0. So our most basic rational function is the reciprocal function, and that's f of x equals 1 over x. So its domain is going to be the set of real numbers except for 0 because we would get 1 over 0. So we're going to go ahead and look at the behavior of f near the value 0 in order to figure out how to graph this. So I have x values here as they approach 0 from the left here. And so I'm approaching this here. I'm getting closer and closer and closer to 0. And these are my y values. So as x approaches 0 from the left, we can see that f of x approaches negative infinity because we go from negative 1 all the way to negative 1,000. So as x approaches 0, and then this minus sign means from the left, f of x approaches negative infinity, or our y values go to negative infinity. So that means that our graph falls. So here's a picture of that. And as x approaches 0 from the right, we have x values here that are getting closer and closer and closer to 0. And so we have our y values here for that. So we can see as we approach 0 from the right, our y values increase. So that means that as x approaches 0 from the right, f of x approaches positive infinity. So we denote this as x approaches 0, and then the plus is from the right, f of x approaches infinity, which means that the graph rises. So now we're going to look at what happens as x gets farther away from the origin, because here we have as x approaches 0 from the right and from the left. So we have these parts, but we're not sure what happens when x gets farther away from the origin or as f of x increases and decreases without bound. So we're going to basically see what happens when x increases without bound and x decreases without bound. So for x increasing, over x values increasing, and we can see that these get smaller and smaller, our y values. And then when x decreases without bound, so we're just going closer and closer to negative infinity, we see that our values become greater. We go from negative 1, which is less than negative 0.001. So as x increases and decreases without bound, the function values of f of x get closer to 0. So as x goes to infinity, f of x goes to 0. And as x goes to negative infinity, f of x goes to 0. So that's like this representation in that graph. And when we take everything, all the parts together, this is what our graph looks like. So we have f of x approaches 0 as x goes to negative infinity. F of x goes to negative infinity as x goes to 0 from the left. We have f of x goes to infinity as x goes to 0 from the right. And f of x goes to 0 as x goes to infinity. And then we have our domain, we know is just all real values except x equals 0. And then our range is also all y values except y equals 0. So here's just some notation that we used to review. So as x approaches a from the right, that's going to be with the plus, and then a from the left is with the minus. And so we say x increases without bound if x is just going to infinity, and x decreases without bound when x goes to negative infinity. Alright, so now we're going to learn about asymptotes. So our definition of a vertical asymptote is the line x equals a of the function y equals f of x if y approaches plus or negative infinity as x approaches a from the right or left. So basically that's saying, here's different pictures of what that, different ways that we could put our graphs having vertical asymptotes. So basically our graphs are going to approach the asymptotes as they're going without bound from the right or left, but they're not going to cross them. So our x equals a is like the wall that the graph doesn't cross, but it just gets closer and closer and closer and closer to it, but never crosses it as our y approaches positive or negative infinity. Alright, so our method of locating vertical asymptotes. So if we have f of x equals p of x over q of x as a rational function, where p of x and q of x have no common factors, so they're reduced to the simplest form, and a is a 0 of q of x, which is the denominator, then x equals a is a vertical asymptote of the graph of f. And that's because if a is a 0, that means that the denominator is going to be 0, right? So that means that it's undefined at that point, which is why we have an asymptote, because those are where it's undefined. So the definition of a horizontal asymptote is the line y equals b of the graph of the function if f of x approaches b as x approaches positive or a negative infinity. So we have here different depictions of our horizontal asymptote. The difference kind of with horizontal asymptotes is that you actually could cross those at some point, which is depicted by this graph here. But also, like, we have our cases here where we're seeing that it's just it's approaching it, but it's never really getting to it as x approaches positive or negative infinity. So this is different than our vertical asymptote, because our vertical asymptote, which was as y approaches positive or negative infinity, here it says as x approaches positive or negative infinity. Alright, so locating our horizontal asymptotes. So we have f as the rational function given by, and we have an, xn, and all that, and bm and xm and all the rest of that. So the degree of our numerator is n, and the degree of our denominator is m. So we have if n is less than m, then the x-axis, or y equals 0 is the horizontal asymptote of f. If n equals m, the line y equals an over bn is the horizontal asymptote of f. So that's basically taking the leading coefficients of our highest degree terms. And then if n is greater than m, the graph of f has no horizontal asymptote. So here for our example, we're going to find the vertical and horizontal asymptotes of 3x squared minus 2x minus 1 over 2x squared plus 3x minus 2. So finding our vertical asymptote, we go ahead and factor the denominator. So I got 2x minus 1 and x plus 2. So our denominator is 0 when x equals 1/2 and x equals -2. So our vertical asymptotes are the lines x equals 1/2 and x equals -2. Our horizontal asymptote, since the degrees of the numerator and denominator are the same, we just go ahead and take the leading coefficients. So we have 3/2. So our horizontal asymptote is the line y equals 3/2. So those are our asymptotes. Okay, now we're going to use transformations to graph rational functions. So we're going to graph and state the domain and range of 2/x minus 3. So we know that our standard rational function is 1/x. So we're going to express r in terms of f. So if we factor out the 2, we have 2 times 1/x minus 3. And then we know that f of x minus 3 would be our 1/x minus 3 if we're plugging this in here for our x of our f of x. And then so we have 2 times f of x minus 3. So that means we're going to shift 3 units to the right and stretch vertically by a factor of 2. So we can see that r of x has a vertical asymptote at x equals 3 and a horizontal asymptote at y equals 0, because horizontal asymptote, if our m is greater than n, so here we have x to the first and here we have x 0 because there's no x, then we have that m is greater than n. So that's why y equals 0 is our horizontal asymptote. And so our domain, we graph the asymptotes here, and we just, we know that 1/x is our graph from up here. So we're matching that graph but transforming it, so we just draw it like that. So it shifted 3 units right and stretched vertically. So our domain is x, where x cannot equal 3. Then our range is y, where y cannot equal 0. Okay, now we're going to state the domain and range and graph 3x plus 5 over x plus 2. So here we can't really see how it's going to be 1/x. So we're going to use long division to divide these. And I'm going to get x plus 2 divided by 3 divided into 3x plus 5. And I get 3 minus 1/x plus 2. So I just switch them and I get minus 1/x plus 2 plus 3. And then I'm comparing this to f of x equals 1/x. So I can see that I have negative on the outside of this, negative f of x plus 2 plus 3. So that means I'm going to shift 2 units left, reflect in the x-axis, and shift up 3 units. So I can see my vertical asymptote is x equals -2, and then my horizontal asymptote is y equals 3. So our asymptotes actually help us graph them, and we're not having to do points and stuff and transform them. We just use our asymptotes. We can see our domain is x such that x does not equal -2, and our range is y such that y does not equal 3, because that's our horizontal asymptote. Okay, so here's some steps on sketching the graphs of rational functions. So our first step is to factor the numerator and denominator. The second step is to find our intercepts, our x and y intercepts. So the x-intercepts are found by determining the zeros of the numerator, and the y-intercepts are from the value of the function at x equals 0. So that I'll show you in the example how to do that. And then our third step is finding the vertical asymptotes. And then we actually do test values on each side of the vertical asymptote and also between the vertical asymptote and the x-intercept to graph the rest of the function. And then we use our horizontal asymptote, and then we plot additional points if we need. So we usually plot points between and beyond each x-intercept and vertical asymptote. Okay, so we're going to go ahead and graph 2x minus 1 over x minus 1. So it's already factored, so we don't have to do that. But we're going to go ahead and find the x and y intercepts. So our y-intercept is when we plug in x equals 0. So I plug that in, and I get 1. So our y-intercept is 0, 1. Our x-intercept, we're solving p of x equals 0, where p of x is the numerator of fx. So we don't have to worry about the denominator. So we do 2x minus 1 equals 0. So we get x equals 1/2. So our x-intercept is 1/2, 0. So our vertical asymptote is we're solving qx, where q of x is the denominator. So I have x minus 1 equals 0. So we have a vertical asymptote at x equals 1. The horizontal asymptote, the numerator and denominator, we can see they have the same degree. So we take the leading coefficient. So we have 2 and 1 are the leading coefficients. So horizontal asymptote is at y equals 2. So my vertical asymptote is 1. And then my x-intercepts 1/2. So I'm plotting points between each x-intercept and vertical asymptote and beyond. So my beyond is going to be 4 and 2, and then my between is my 3/4, and then beyond in the other direction is -1 and -2. So like my VA is like here, my 0 is like here. So I'm just plotting points between and beyond each. So then I plug those points in to my function, and I get those points. So on the graph, I do my asymptotes first. So I have my vertical and horizontal asymptotes. I'm plotting my y-intercept and my x-intercept, and then I plotted the points that I found, and I just connect the dots. And I know it's going to be in that shape because the points are just going to go like towards the asymptote, and then they turn away and go towards infinity and close to the center where their asymptotes intersect. So that's my graph. Okay, now I'm going to graph 2x squared plus 7x minus 4. And this is over x squared plus x minus 2. And then we're going to state the domain and range. So my first step is I'm going to factor. So I have 2x minus 1 times x plus 4 over x minus 1 times x plus 2. And I factored here on the side. Make sure you look at that and know that it makes sense. Know that you're able to do that because our coefficient isn't 1 here. So the factoring is a little bit different. And we know our x-intercept is going to be 2x minus 1 equals 0 and x plus 4 equals 0. So our x-intercepts are 1/2 and -4 using solving the numerator. Our y-intercept, when we plug in 0, is going to be 2. And then our vertical asymptote is when the denominator is 0. So I have x minus 1 equals 0 and x plus 2 equals 0. So I have vertical asymptotes at 1 and -2. So I test on each side of the vertical asymptote if y is going to infinity or if y is going to go -infinity using test values. And then I check if y is positive to the left and right of x equals 1 of our vertical asymptote. And I do, and x equals -2. Our horizontal asymptote, the degree of the numerator and denominator are the same, so we take leading coefficients. So our horizontal asymptote is y equals 2. So I test points between and beyond the vertical asymptote and x-intercepts. So my x-intercept is, I think I forgot one of them, 1/2. And x equals -4. Now my vertical asymptotes 1 and -2. Alright, so I'm testing points. So my vertical asymptote would be like here, and then here, and then my x-intercepts are going to be here as well, and then here. So I'm testing points between and beyond. So those are the points I get. So I go ahead and I plot my horizontal asymptote, my vertical asymptotes, and then the points that I found. And then I do my graph. So I could probably do like another point here if I wanted to, or solve for it if I didn't know where, if I connected those and I didn't know where it went. But those are the points that I get, and then this can cross the horizontal asymptote there. So that's the graph that I get using the points in my asymptotes. Okay, so here we have the ability to cancel some things with common factors in the numerator and denominator. So if we have p of x over q of x, and if p and q have a factor in common, we could cancel that factor for values of x where the factor is not 0. And so the reason why is because as division by 0 is undefined at those values of x, we're not really canceling it. And so it has a hole at those points. So it was never there kind of thing, because that's what makes the function undefined. But here's an example of x minus 3 over x squared minus 3x. I could factor the bottom by factoring out an x. So I have the common factor of x minus 3 on the numerator and the denominator. I could cancel those and I'm left with 1 over x. However, notice how my x minus 3, it's 0 when x equals 3. And we know that we have a hole then at x equals 3 since we canceled them. Okay, so when I graph it, I basically just put an open dot at the hole. So s of x equals 1 over x for x not equal to 3. Where's our hole? Okay, now we're going to go over slant asymptotes and end behavior. So r of x is p of x over q of x. So if the degree of the numerator is 1 more than the degree of the denominator, we have a slant asymptote. And we can find it using division. So we would basically have r of x equals ax plus b plus r of x over q of x. So we'd have ax plus b is our slant asymptote. So let's do an example so we could see that and understand what's going on. So we're going to graph x squared minus 4x minus 5 over x minus 3. So we're going through our steps. So we factor. So I factor the top, and I get x plus 1 times x minus 5 over x minus 3. So our intercept